We're looking at algebra tiles, and we're going to look at how we can use these algebra tiles to help us represent some algebraic concepts. So just to define these tiles, the positive tiles are going to be represented by these squares, the large squares, and the x squared is the area. Same with x. The algebra tile values, x squared and x, represent the areas of these tiles. So the length of this tile is x, the width of this tile is x, and the area is x squared. So it's important to understand when we're dealing with the length and width, or the products or the factors, versus the product or the actual calculation, okay, which is x squared. So here the area is x, the length is 1, the width is x. Okay, so it's important to, again, to recognize the length and width of this. And for the negative ones, it's just all going to be the opposite. We're going to have length of x, width of x. The area is going to be negative x squared. And here again, the area here is negative x squared. The length is 1, width is x. So these colors are kind of arbitrary. And for the most part, as long as you're consistent with how you label these. Okay, I've tried to keep these colors consistent with the textbook. However, if you want to just keep, when you do these on your own, you either shade or don't shade and keep one of them positive and the other one negative. And just as long as you're consistent with it, I'll be able to tell if it's being done correctly. So these are our variable tiles. Okay, our small tiles are going to have an area of 1, which means that they have a length of 1, a width of 1. Okay, and the red squares are going to, little red squares are going to represent negatives. And it's important to understand that we cannot line up a bunch of 1's tiles along the x. It won't match. Okay, and it's done for a purpose, because we don't want to ever say that there's some number of 1's that will match up with the x tile here, the length along x. Okay, so please try not to arrange your tiles in that way. We always make the edges that match up with each other. Okay, so here we have an algebraic expression, x squared plus 2x minus 1. There are 3 different types of terms here, and the like terms we can combine together. And the like terms are going to be represented by the same shape. So we have 3x squared, so we have 3 of these x squareds. We have 2x tiles, which are different from the x squareds, so they have a different shape. So we have these 2 x's. And then the negative 1 is not only a different shape, but it's also a different color because of the negative involved. So this is how we're going to define these tiles. So when we have these expressions here, we want to be able to show them with tiles. So since we probably don't have color, if you have color, that's great, but if you don't have color, we're just going to draw these tiles as shaded as positive and white as negative. So there's an x squared tile. Okay, we're just going to shade that in. And since it's 2x squareds, we have 2 groups of x squareds. So we're going to have it look like that. We have 1x. Okay, so that we have to use a different shape for that. We're going to shade that in for positive, and then we have 5 1's tiles. Again, they are different. It's a different term, so we need a different shape for that. And then we're going to have 5 of those. Okay, so these, although it says x squared, x, really we're just counting the number of shapes. So same thing here. We have 1x squared, so I'm going to draw 1 square, 1 large square, and I'm going to shade it to indicate that that one is positive. Oh, sorry, yeah. And this one here is going to be 3 x's. So I'm going to arrange this 3 x's like this. And I have 2 1's tiles. Now, we should really use algebra tiles, because then with algebra tiles we can rearrange them into different shapes. And really what we're looking at is, can these be arranged into rectangles? Because rectangles are a nice regular shape, and rectangles allow us to see if there's a length and width. Or, in other words, is it factorable? So, if I were to rearrange these tiles, I could maybe rearrange these tiles like this. I can put this edge length, again, we only put the x's edges together and the 1's edges together, but since we can arrange it like that, we can actually put the 1's tiles here, so note that the 1's edges match here on the width and length, and we can actually put all our tiles in a rectangular shape. The nice thing about that is, if it's a rectangular shape, we know that this has a length and width, and if it has a length and width, we can write it as multiplication, because these are the area pieces. Yeah, I've got the area of x squared plus 3x plus 2. That can be made by using a length and width. And the length along this edge here is going to be x. Remember that the area is x squared, so the length and width is x here. So along the vertical, I have x and I have 1. So it's going to be x plus 1. Along the horizontal, I have x and then I have 1 and 1. Okay, so along that horizontal, I have x plus 2. So if I were to write this as a multiplication, I could write this as x plus 1 times x plus 2. Okay, these are factors now because I've grouped them into brackets. And that multiplication of length times width gives me an area of x squared plus 3x plus 2. So I'm just going to write this in. This is my length times width, and that must equal my area. Okay, remember we defined these tiles, x squared, 3x, and 2, as the area pieces. So there it is. We are able to arrange these tiles in rectangles. And since we can arrange in rectangles, that means that this area or shape is factorable.